Good morning. I want to give you guys some additional information on work and power and kind of do an example problem with you guys in order to help us out with an activity we're going to do today. So let's get started. First thing we want is some definitions and important equations. So work is the change in energy of a system. So if we have energy leaving our system, that means that work is being done by our system. That's negative work. Or if work is being done on our system, energy is entering our system, and that would be positive work, right? So we have work is equal to force times distance times cosine theta is our formula. If your force and your direction are the same direction, and your force and motion are the same direction, then if I'm like pushing a box forward and it's actually moving forward, then my theta is 0, so cosine of 0 is equal to 1, so we don't have to worry about the cosine theta. You would need to worry about the angle of your motion and your force, and maybe a problem like if you're pulling a box by a rope and the rope is at an angle, then you have force being pulled at an angle, but the distance is, your direction of motion is either forward or backwards, so you have to think about it then. We're not going to think about it today. Power is the change in work or energy per time. So power, P equals E over T. So energy, that could be any form of energy, total energy, whatever you need for your problem, you plug that in. And then also work per time, so that FD cosine theta divided by time. Power is also equal to force times velocity. I have an example problem. I'll read it, and then I got to move to another place to do it. I've learned the hard way. This is like my 12th take. So a box with a mass of 0.5 kilograms is sliding along the floor at 10 meters per second, slowing to a stop. The coefficient of friction between the floor and the box is 0.23. We want to first find the thermal energy of the system, and second thing we want to find is how far the box traveled before stopping. So let's do that first part. I'm going to go over here, and I have everything written out. You're just going to have to remember. All right. So we have, first we want to do is draw an LOL. And we have in our system that box. We have the floor, that's an F, and then the earth, right? Since my box is moving, I know I have a kinetic energy at the beginning, but it's stopped at the end, so there's no kinetic energy at the end. There's no change in height for us to account for, so there's no gravitational potential energy the entire time. There's no springs anywhere, so no US. But we do know that there's an E therm, because the problem told us. Oops. These are supposed to be the same height. Let's fix that. That seems important. So that means that all of our energy from before is going to be thermal energy. So if I'm going to make a conservation of energy equation, it's going to be K equals E therm. Hey, we're done. All we have to do is just find out what kinetic energy is, and then we'll know what the thermal energy is. Our formula for kinetic energy is 1/2 mv squared, and that's going to be equal to E therm. So I just plug in values. 1/2, my mass is 0.5 kilograms. My velocity is 10 meters per second. Don't forget to square it. So that's going to give me a thermal energy of 25 joules. Fabulous. So in this case, it made sense, since I was looking for thermal energy, to have the floor, that rough floor, in my system, all right? So now we're going to do the next part of the problem, and we're going to need to actually move some things out of the system. So let's start over, start fresh, and we want a new LOL. And I'm going to show you how to do this. So since we are looking for a distance traveled, that's kind of a clue to me that I'm going to need work involved in this somehow. And I still have the same initial setup. I still have all this kinetic energy, and I still don't have any height or spring energy. But now I don't want to have any thermal energy. I want all of that energy that was thermal in our initial scenario. I want that to be work done by our system. So I have energy leaving the system. And I'm going to account this to the rough floor. So I'm going to say this is the floor's fault. So we still have the earth and our box in the system, but now the floor is out of the system. So that means we have no kinetic, no UG, no US, and no E therm. Whenever your LOL diagram looks like this, where you have energy before, none after, that means work has happened. Or if you have the opposite, where you have no energy before and you end up with energy at the end, that means that work has happened. Okay, so let's set up our scenario. So we still have K on one side, and that's going to be equal to work. Okay, let's plug in our base formulas. 1/2 mv squared is equal to force times distance times cosine theta. Let's clean up this work formula to make it a little easier for us to work with. So we know our theta is 0 degrees. So cosine of theta is going to be equal to 1. So we can cancel, well, not cancel, we can erase that, not have to think about it. It's just multiplied by 1. And this force, that's that force due to friction. So that's equal to Ff, which is going to be equal to force normal times mu. So thinking about what our force normal should be, well, if we drew an FBD, then we'd have Fg pointing down, Fn pointing up, and then force friction pulling back. Wow, I hope y'all can interpret my chicken scratch today. So I can tell this is balanced because it's just staying on the same plane. We didn't have any change in height. So we know that Fn is equal to Fg. So Fn is equal to mg, all stuff we've seen and used before. So that means that F, that in our formula for work, is going to be equal to mu times mg. Let's go back and clean this up. 1/2 mv squared is equal to mu mg d. We're trying to find d. We are looking for that distance. So algebraically, let's solve for d. So that means it's going to end up being mv squared divided by 2 mu mg, and that equals d. Hey, look, mass cancels. So you're probably thinking, couldn't I just solve this with forces? And you probably could have. But let's say you didn't know the mass, then energy would be the way to go because the energy ends up canceling out. So this means our final formula for D is V squared over 2 mu G. Plug in some values, 10 squared, 2.23, 9.8 for G. And that means that distance is going to be 22.18 meters. All right, so that's just an example of how to solve a work problem for conservation of energy. Now let's incorporate power a little bit. So if, let's say, I wanted to know the power of our system, how much energy was being changed per time. I'm going to erase some of this stuff. Or I'm just going to erase all of it. We're just going to say goodbye. So if I want to look for the power, that's going to be my work per time. So remember, our work in this case was that mu mg d divided by time. So if I wanted the power, let's say this took 5 seconds to occur. I already know everything else because we just solved for d. So mu is 0.23, m is 0.5, g is 9.8, d is 22.18. And divide that by 5 seconds. Plug this into the calculator. I didn't do this part before. 2.23 times 0.5 times 9.8 times 22.18 divided by 5 is roughly 5. Now you're thinking, what is my unit? Well, work is measured in joules, time is measured in seconds, so joules per second, or joules per second, that is the same thing as a watt. So this is roughly 5 watts of power that went into transferring that box across the floor. Okay, hopefully this has been helpful. I hope you can see that the power really isn't that hard. Once you know everything else, then power is just like a little cherry on top. Okay, let's get on with the